Well, welcome back to our course, Computer Organization and Architecture. We're going to be talking about the control unit operation and microprogramming control. This is the last of a series of lectures that we have been focusing on the central processing unit, getting a deeper perspective on what it's doing. And so hopefully you're going to see in earnest the kind of complexity that is in this component, as well as many other things that we have been discussing in terms of how to improve performance in one way or another. So let's go ahead and talk about what we're going to cover. We're going to get into what are the micro operations of fetch, indirect, interrupt, execute, and instruction cycles. We'll talk about the microprogram control, talk about the micro instructions, the microprogram control unit, Wilks control, advantages and disadvantages of microprogram control. We'll talk about control of the processor, and then we'll finally talk about hardwired implementations. So we have seen that the operation of a computer in executing a program, what it does is there's consists of a sequence of instruction cycles with one machine instruction per cycle. Of course, we must remember that this sequence of instruction cycles is not necessarily the same as the written sequence of instructions that make up the program because of the existence of branching instructions. And so this is one of the innovations that we've been talking about as we get into the deeper parts of thinking about a central processing unit, and it continuing to try and come with more innovative ways to improve performance. What we are referring to here is the execution time sequence of instructions. We have further seen that each instruction cycle is made up of a number of smaller units. One subdivision that we found convenient is fetch, indirect, execute, and interrupt, with only fetch and execute cycles always occurring. To design a control unit, however, we need to break down the description further. In our discussion of pipelining in Chapter 16, we began to see that a further decomposition is possible. In fact, we will see that each of these smaller cycles involves a series of steps, each of which involves a processor registers. We will refer to these steps as micro operations. The prefix micro refers to the fact that each step is very simple and accomplishes very little. So micro operations are the functional or atomic operations of a processor. So in this section, we will examine micro operations to gain an understanding of how the events of any instruction cycle can be described as a sequence of such micro operations. A simple example will be used. In the remainder of this chapter, we will then show the concept of micro operations serves as a guide to the design of the control unit. So here in figure 19.1, it depicts a relationship among the various concepts we have been discussing. To summarize, the execution of a program consists of a sequence of the execution of instructions. Each instruction is executed during an instruction cycle made up of shorter cycles. For example, fetch, indirect, execute, and interrupt. The execution of each subcycle involves one or more shorter operation, that is micro operations. And so this is where we're just trying to get an illustration down here. We're just seeing that there's multiple layers, and we're getting it down to the lowest level that we're going to be covering for what we're talking about for a central processing unit. We begin by looking at the fetch cycle, which occurs at the beginning of each instruction cycle and causes an instruction to be fetched from memory. For purposes of discussion, we assume the organization depicted in figure 16.5, the data flow fetch cycle. And so you may want to go back and check that out if you want to remind yourself of that. So the 4 registers are involved. The memory address register, the MAR, it contains It is connected to the address lines of the system bus. It specifies the address in memory for a read or write operation. Then there's the memory buffer register. It is connected to the data lines of the system bus. It contains the value to be stored in memory or the last value read from memory. Then we have the program counter, which holds the address of the next instruction to be fetched. And finally, we have the instruction register, which holds the last instruction fetched. So let's look at a sequence of events for the fetch cycle from the point of view of its effect on the processor register. An example appears in figure 19.2. At the beginning of the fetch cycle, the address of the next instruction to be executed is in the program counter. In this case, the address is 1100-100. The first step is to move that address to the memory address register, the MAR, because this is the only register connected to the address lines of the system bus. The second step is to bring in the instruction. The desired address in the MAR is placed on the address bus. The control unit issues a read command on the control bus, and the result appears on the data bus and is copied into the memory buffer register, the MBR. We also need to increment the PC by the instruction length to get ready for the next instruction. Because these two actions, read word from memory and increment PC, do not interfere with each other, we can do them simultaneously to save time. This third step is to move the contents of the MBR to the instruction register. This frees up the MBR for use during a possible indirect cycle. Thus, the simple fetch cycle actually consists of 3 steps and 4 micro instructions. Each micro instruction involves the movement of data into or out of a register. So long as these movements do not interfere with one another, several of them can be placed during one step, saving time. So once an instruction is fetched, the next step is to fetch source operands. Connecting our simple example, let us assume a one address instruction format with direct and indirect addressing allowed. If the instruction specifies an indirect address, then an indirect cycle must precede the execution cycle. The data flow differs somewhat from that indicated in figure 16.6, the data flow in the indirect cycle, and includes the following micro operations. So it moves into the MAR, the IR, moves an address into the IR. This happens at time 1. At time 2, the memory is moved into the MBR, and at time 3, the address that was in the MBR is moved into the IR. So the address field of the instruction is transferred to the MAR. This is then used to fetch the address of the operand. Finally, the address field of the IR is updated from the MBR so that it now contains a direct rather than an indirect address. The IR is now in the same state as if indirect addressing had not been used, and it is ready for the execution cycle. We skip that cycle for a moment to consider the interrupt cycle. Okay, I paused the video for a minute, and these were the 3 things that I was mentioning, trying to do it verbally. I figured it'd probably be easier if I just put this down. And so these are the 3 micro operations, T1, at T2, T1 and T2 and T3. So I'll continue on here. So here we have the interrupt cycle. Okay, so continuing with the interrupt cycle, let me backtrack a little bit here. At the completion of the execute cycle, a test is made to determine whether any enabled interrupts have occurred. If so, the interrupt cycle occurs. The nature of this cycle varies greatly from one machine to another. We present a very simple illustration of sequences from figures 16.7, the data flow indirect cycle. And so I've put these things like I did on the last slide down on the bottom corner here, bottom right corner of what I'm mentioning. So we have a T1, the program counter. It's going to be putting contents into the MBR. At time 2, the save address is going to be pushed into the MAR. The routine address is going to be connecting to the program counter, and at time 3, we're going to be putting the reference from the MBR into memory. So this is something you can keep in mind. So in the first step, the contents of the PC are transferred to the MBR. So we see that. So that they can be saved for return from the interrupt. Then the MAR is loaded with the address at which the contents of the PC are to be saved, and the PC is loaded with the address of the start of the interrupt processing routine. These two actions may each be a single micro operation. However, because most processors provide multiple types and or levels of interrupts, it may take one or more additional micro operations to obtain the save address and the routine address before they can be transferred to the MAR and PC respectively. In any case, once this is done, the final step is to store the MBR, which contains the old value of the PC in the memory. The processor is now ready to begin the next instruction cycle. The fetch, indirect, and interrupt cycles are simple and predictable. Each involves a small fixed sequence of micro operations, and in each case, the same micro operations are repeated each time around. This is not true of the execute cycle because of the variety of opcodes. There are a number of different sequences of micro operations that can occur. The control unit examines the opcode and generates a sequence of micro operations based on the value of the opcode. This is referred to as an instruction decoding. Let us consider several hypothetical examples. First, consider an add instruction. So that's what I'm showing here down in the lower right corner, so you can see which I'm referring to, which add the contents of location X to register R1. The following sequence of micro operations might occur. So those are listed here for time 1, time 2, and time 3. So we begin with the IR containing the add instruction. In the first step, the address portion of the IR is loaded into the MAR. Then the reference memory location is read. Finally, the contents of R1 and MBR are added by the ALU. Again, this is a simple example. Additional micro operations may be required to extract the register reference from the IR and perhaps to stage the AL input of the output in some intermediate registers. So we're seeing just some examples. We're going to this next level below the opcodes to the micro operations and just going through those stages. So we have seen that each phase of the instruction cycle can be decomposed into a sequence of elementary micro operations. In our example, there is one sequence each for the fetch, indirect, and interrupt cycles, and for the execute cycle, there is one sequence of micro operations for each opcode. To complete the picture, we need to tie sequences of micro operations together, and this is done in figure 19.3, which we're showing here. We assume a new 2-bit register called the instruction cycle code, or ICC. The ICC designates the state of the processor in terms of which portion of the cycle it is in. So 00 is fetch, 01 is indirect, 10 is execute, and 11 is interrupt. At the end of each of the 4 cycles, the ICC is set appropriately. The indirect cycle is always followed by the execute cycle. The interrupt cycle is always followed by the fetch cycle. And so you can refer back to figure 16.3 for the instruction cycle. For both the fetch and the execute cycle, the next cycle depends on the state of the system. That's a flow chart of figure 19.3 here, defines a complete sequence of microoperations depending only on the instruction sequence and the interrupt patterns. Of course, this is a simplified example. The flow chart for an actual processor would be more complex. In any case, we have reached the point in our discussion in which the operation of the processor is defined as the performance of a sequence of microoperations. We can now consider how the control unit causes a sequence to occur. As a result of our analysis in the preceding section, we have decomposed the behavior of functional of the behavior or functioning of the processor into elementary operations called microoperations. By reducing the operation of the processor to its most fundamental level, we're able to define exactly what it is that the control unit must cause to happen. Thus, we can define the functional requirements for the control unit, those functions that the control unit must perform. A definition of these functional requirements is the basis for the design and implementation of the control unit. We have information at hand. The following three-step process leads to a characterization of the control unit. 1, define the basic elements of the processor. 2, describe the micro operations that the processor performs. And 3, determine the functions that the control unit must perform to cause the micro operations to be performed. We have already performed steps 1 and 2, so let us summarize the result. First, the basic functional elements of the processor are the following: the arithmetic logic unit, the registers, the internal data path, the external data path, and the control unit. Some thought should convince you that this is a complete list. The ALU is the functional essence of the computer. Registers are used to store data interrupt to the processor. Some registers contain status information needed to manage instruction sequences, like a program status word. Others contain data that go to or come from the arithmetic logic unit, the memory, the input and output modules. Internal data paths are used to move data between registers and between register and arithmetic logic unit. External data path links registers to memory and I/O modules, often by means of a system bus. The control unit causes operations to happen within the processor. The execution of a program consists of operations involving these processor elements. As we have seen, these operations consist of a sequence of microoperations. Upon review of section 19.1, the reader should see that all microoperations fall into one of the following categories: transfer data from one register to another, transfer data from a register to an external interface, for example, a system bus, transfer data from an external interface to a register, perform an arithmetic or logic operation using registers for input and outputs. All of the micro operations needed to perform one instruction cycle, including all of the micro operations to execute every instruction in the instruction set, fall into one of these categories. It can now be somewhat more explicit about the way in which the control unit functions. The control unit performs 2 basic tasks: sequencing, that the control unit causes the processor to step through a series of micro operations in the proper sequence based on the program being executed. Execution, the control unit causes each micro operation to be performed. The preceding is a functional description of what the control unit does. The key is to how the control unit operates is the use of control signals. So we have defined the elements that make up the processor and the arithmetic logic unit, registers, data paths, and the micro operations that are performed. For the control unit to perform its function, It must have inputs that allow it to determine the state of the system and outputs that allow it to control the behavior of the system. These are the external specifications of the control unit. Internally, the control unit must have the logic required to perform its sequencing and execution functions. We defer a discussion of the internal operation of the control unit to section 19.3 and chapter 19.4. So we'll be coming back to this. So the remainder of what we're going to focus on now is concerned with the interactions between the control unit and the other elements of the processor. Figure 19.4 is a general mode of the control unit showing all of the inputs and outputs. The inputs are the clock. This is how the control unit keeps time. The control unit causes one micro-operation or a set of simultaneous micro-operations to be performed for each clock pulse. This is sometimes referred to as the processor cycle time or the clock cycle time. There's the instruction register. The opcode and addressing mode of the current instruction are used to determine which micro-operations to perform during the execute cycle. Flags, these are needed by the control unit to determine the status of the processor and the outcome of the previous ALU operations. For example, for the increment and skip if zero instruction, the control unit will increment the PC if the zero flag is set. The control signals from control bus, the control bus portion of the system bus provides signals for the control unit. The outputs are as follows. The control signals within the processor, these are two types, those that cause data to be moved from one register to another and those that activate specific ALU functions. Control signals to control buses. These are of two types, the control signals to memory and control signals to the I/O modules. Three types of control signals are used, those that activate an ALU function, those that activate a data path, and those that are signals on the external system bus or other external interface. All of these signals are ultimately applied directly as binary inputs to individual logic gates. Let us consider again the fetch cycle to see how the control unit maintains control. The control unit keeps track of what is in the instruction cycle. At a given point, it knows that the fetch cycle is to be performed next. The first step is to transfer the contents of the PC to the MAR. The control unit does this by activating the control signals that opens the gates between the bits of the PC and the bits of the MAR. The next step is to read a word from memory into the MAR and increment the PC, and increment the PC. The control unit does this by sending the following control signals simultaneously. A control signal that opens gates allows the contents of the MAR onto the address bus. A memory read control signal on the control bus. A control signal that opens the gates allowing the contents of the data bus to be stored in the MBR. Control signals to logic that add 1 to the contents of the PC and store the result back in the PC. Finally, the control unit sends a control signal that opens gates between the MBR and the IR. This completes the fetch cycle, except for one thing. The control unit must decide whether to perform an indirect cycle or an execute cycle next. To decide this, it examines the IR to see if an indirect memory reference is made. The indirect and interrupt cycles work similarly. For the execute cycle, the control unit begins by examining the opcode and on the basis of that decide which sequence of micro operations to perform for the execute cycle. So to illustrate the functioning of the control unit, we can examine a simple example. Figure 19.5 illustrates the example. This is a simple processor with a single accumulator. The data paths between elements are indicated. The control path for signals emanating from the control unit are not shown. but the terminations of control signals are labeled C, CI, so C something, C0, all the way up to C12. The control unit receives inputs from the clock, the IR, and the flags. With each clock cycle, the control unit reads all of the inputs and emits a set of control signals. Control signals go to the three separate destinations. The data path, the control unit controls the internal flow of data. For example, on instruction fetch, the contents of the memory buffer register are transferred to the IR. For each path to be controlled, there is a switch, which is indicated by a circle in the figure. A control signal from the control unit temporarily opens the gate to let data pass. For the arithmetic logic unit, the control unit controls the operation of the ALU by a set of control signals. These signals activate various logic circuits and gates within the ALU. And there's the system bus. The control unit sends control signals out onto the control lines of the system bus. For example, a memory read. The control unit must maintain knowledge of where it is in the instruction cycle. Using this knowledge and by reading all of the inputs, the control unit emits a sequence of control signals that causes micro operations to occur. It uses the clock pulses to time the sequence of events, allowing time between events for signal levels to stabilize. Table 19.1 indicates the control signal that are needed for some of the micro-operation sequences described earlier. For simplicity, the data control paths for incrementing the PC and for loading the fixed address into the PC and MAR are not shown. It is worth pondering the minimal nature of the control unit. The control unit is the engine that runs the entire computer. It does this based only on knowledge of the instructions to be executed and the nature of the results of the arithmetic and logical operations. Things like positive, or if it's something that's overflowed or something like that. It never gets to see the data being processed or the actual results produced. And it controls everything within a few control signals to points within the processor and a few control signals to the system bus. Figure 19.5 indicates the use of a variety of data paths. The complexity of this type of organization should be clear. More typically, some sort of internal bus arrangement, as was suggested in figure 16.1 for the internal structure of a CPU, will be used. And so we're not going to go back there, but if you want, you can go back to that chapter and look at that figure. Using an internal processor bus, figure 19.5 can be rearranged as shown in figure 19.6. A single internal bus connects the ALU and all processor registers. Gates and control signals are provided for movement of data onto and off the bus from each register. Additional control signals control data transfer to and from the system, that is the external bus, and the operations of the ALU. Two new registers labeled Y and Z have been added to the organization. These are needed for the proper operation of the ALU. When an operation involving two operands is performed, one can be obtained from the internal bus, but the other must be obtained from the other source. The AC could be used for this purpose, but this limits the flexibility of the system and would not work with a processor with multiple general purpose registers. Register Y provides temporary storage for the other input. The ALU is a combinatorial circuit, so this is something that we talked about in chapter 12 with no internal storage. Thus, when control signals activate an ALU function, the input to the ALU is transferred to the output. Therefore, the output of the ALU cannot be directly connected to the bus because this output would feed back to the input. So the arithmetic logic unit, remember combinational circuits, we can reprogram the ALU with a command And so that's one of the novelties of what's going on with the ALU. So to illustrate some of the concepts introduced thus far in this chapter, let us consider the Intel 8085. Its organization is shown in figure 19.7, which we're illustrating here. Several key components that may not be self-explanatory are the increment and decrement address latch, this is the logic that can add one or subtract one from the contents of the stack pointer to or program counter. This saves time by avoiding the use of the arithmetic logic unit for this purpose. There's the interrupt control. This module handles multiple levels of interrupt signals. And then the serial I/O control. This module interfaces to devices that communicate one bit at a time. So this is before the x86 architecture. So you had the 85 and then the 86, and then you have the 86, the 286, 386, 486, 586, which was renamed the Pentium. And thus we go on from there. Table 19.2 describes the internal signals into and out of the 8085. These are linked to the external system bus. And so I'm not going to be reading all of these, but you can pause the video and go through this. But you will see some linkage between this and things that we have been discussing for the x86 architecture. But as a precursor to that, and so things are not quite as developed. Here is the second part, and so these are just more different types of external signals that are going on. And then finally, we have what the pin configuration was for the 8085. So these signals are the interfaces between the 8085 processor and the rest of the system. So this is where those things that we just talked about would show up for the pinout for this chip. The control unit is identified as having two components labeled: one, instruction decoder and machine cycle encoding, and two, timing and control. The discussion of the first component is deferred until the next section. The essence of the control unit is the timing and control module. The module includes a clock and accepts as inputs the current instruction and some external control signals. Its output consists of control signals to the other components of the processor plus control signals to the external system bus. The timing of processor operations is synchronized by the clock and controlled by the control unit with control signals. Each control cycle is divided into from 1 to 5 machine cycles. Each machine cycle is in turn divided into from 3 to 5 stages. Each state lasts 1 clock cycle. During a state, the processor performs one or a set of simultaneous micro operations as determined by the control signals. The number of machine cycles is fixed for a given instruction, but varies from one instruction to another. Machine cycles are defined to be equivalent to bus accesses. Thus, the number of machine cycles for an instruction depends on the number of times the processor must communicate with external devices. For example, if an instruction consists of 8-bit portions, then 2 machine cycles are required to fetch the instruction. If that instruction involves a 1-byte memory or I/O operation, then a 3rd machine cycle is required for the execution. Figure 19.9 gives an example of the 8085 timing, showing the value of external control signals. Of course, at the same time, the control unit generates internal control signals that control the internal data transfer. The diagram shows the instruction cycle for an out instruction. 3 machine cycles, M1, M2, M3, are needed. During the first, the out instruction is fetched. The second machine cycle fetches the second half of the instruction, which contains the number of the I/O device selected for output. During the third cycle, the contents of the AC are written out to the selected device over the data bus. The address latch enable pulse signals the start of each machine cycle from the control unit. The address latch enable or ALE pulse alerts external circuits during time status T1 of machine cycle M1. The control unit sets the IO/M signal to indicate that this is a memory operation. Also, the control unit causes the contents of the PC to be placed on the address bus. So A15 through A8 and the address/data bus A7 through AD0. With the falling edge of the ALE pulse, the other modules on the bus store the address. During time T2, the address memory module places the contents of the address memory location on the address/data bus. The control unit sets the read control signal to indicate a read, but it waits until T3 to copy the data from the bus. This gives the memory module time to put the data on the bus and for the signal levels to stabilize. The final state T4 is a bus idle time during which the processor decodes the instruction. The remaining machine cycles proceed in a similar fashion. Well, we haven't talked about this type of a timing diagram before, but hopefully you're seeing here. First, we have the instruction fetch, the memory read, and the output write. And so it's divided up in those three things as we talked, M1, M2, and M3. So you can pause the video and look over that a little bit longer if you would like. So for the control unit implementation, we have discussed the control unit in terms of its inputs, outputs, and functions. We now turn to the topic for control unit implementation. A wide variety of techniques have been used. Most of these fall into one or two categories: hardwired implementation and micro-programmed implementation. So you have a hardware-centric and more of a software-centric view. In a hardwired implementation, the control unit is essentially a state machine circuit. Its input logic signals are transformed into a set of output logic signals, which are the control signals. The approach is examined in what we're going to be talking about in this section, and microprogrammed implementation is the subject of 19.4, which will come after we're done with this. So figure 19.4 depicts the control unit as we have so far discussed. The key inputs are the IR, the clock, flags, and control bus lines. In the case of the flags and control bus signals, each individual bit typically has some meaning, for example, overflow. The other two inputs, however, are not directly useful to the control unit. First, consider the IR. The control unit makes use of the opcode and will perform different actions, issue a different combination of control signals, that is, for different instructions. To simplify the control unit logic, there should be a unique logic input for each opcode. This function can be performed by a decoder, which takes an encoded input and produces a single output. In general, a decoder will have n binary inputs and 2 to the n binary outputs. Each of the 2 to the n different input patterns will activate a single unique output. Table 19.3 is an example for n equals 4. The decoder for a control unit will typically have to be more complex than that to account for variable length opcodes. An example of the digital logic used to implement a decoder is presented in chapter 12. So if you were interested, you could go back there and review that. The clock portion of the control unit issues a repetitive sequence of pulses. This is useful for measuring the duration of micro-operations. Essentially, the period of the clock pulses must be long enough to allow the propagation of the signals along the data path and through processor circuitry. However, as we have seen, the control unit emits different control signals at different time units within a single instruction cycle. Thus, we would like a counter as input to the control unit with a different control signal being used for T1, T2, and so forth. At the end of the instruction cycle, the control unit must feed back to the counter to reinitialize it at T1. With these two refinements, the control unit can be depicted as shown here in figure 1910. Okay, for microprogram control, the term microprogram was first coined by Wilkes in the early 1950s. Wilkes proposed an approach to control unit design that was organized and systematic and avoided the complexities of a hardware implementation. The idea intrigued many researchers, but appeared unworkable because it would require a fast, relatively inexpensive control memory. The state of the microprogramming art was reviewed in 1964. No microprogram system was wide used at that time. And one of the other papers that explored this summarized the then popular view that the future of microprogramming is, quote, is somewhat cloudy. None of the major manufacturers has evidence interest in the technique, although presumably all have examined it. The situation changed dramatically within a very few months. IBM's 360 was announced in April, and all but the largest models were microprogrammed. Although the 360 series predated the availability of semiconductor ROM, the advantages of microprogramming were compelling enough for IBM to make the move. Microprogramming became a popular technique for implementing the control unit of CISC processors. In recent years, microprogramming has become less used, but remains a tool available to computer designers. For example, as we have seen on the Pentium 4, machine instructions are converted into a RISC-like format, most of which are executed without the use of microprogramming. However, some of the instructions are executed using microprogramming. The control unit seems a reasonably simple device. Nevertheless, to implement a control unit as an interconnection of basic logic elements is no easy task. The design must include logic for sequencing through microoperations, for executing microoperations, for interpreting microcodes, and for making decisions based on ALU flags. It is difficult to design and test such a piece of hardware. Furthermore, the design is relatively flexible. For example, it is difficult to change the design if one wishes to add a new machine instruction. An alternative, which has been used in many CISC processors, is to implement a microprogram control unit. So that's something that the CISC processors are proficient in using. Consider table 19.4. In addition to the use of control signals, each micro operation is described in symbolic notation. This notation looks suspiciously like a programming language. In fact, it is a language known as microprogramming language. Each line describes a set of micro operations occurring at one time and is known as a micro instruction. A sequence of instruction is known as a microprogram or firmware. This later term reflects the fact that a microprogram is midway between hardware and software. It is easier to design it in firmware than hardware, but it's more difficult to write a firmware program than a software program. So you may have heard of firmware and updating your firmware. Well, here's an example of where that starts to play out. How can we use the concept of microprogramming to implement a control unit? Consider that for each micro operation, all the control unit is allowed to do is to generate a set of control signals. Thus, for any micro operation, each control line emanating from the control unit is either on or off. The condition can, of course, be representing a binary digit for each control line. So we could construct a control word in which each bit represents one control line. Then each micro operation would be represented by a different pattern of ones and zeros in the control word. Suppose we string together a sequence of control words to represent the sequence of microoperations performed by the control unit. Next, we must recognize that the sequence of microoperations is not fixed. Sometimes we have an indirect cycle, sometimes we do not. So let us put our control word in a memory with each word having a unique address. Now add an address field to each control word, indicating the location of the next control word to be executed if a certain condition is true. Also add a few bits to specify the conditions. The result is known as a horizontal micro instruction, an example which is shown in figure 1912A on the top of this figure. The format of a micro instruction or control word is as follows. There is one bit for each internal processor control line and one bit for each system bus control line. There is a condition field indicating the condition under which there should be a branch, and there is a field with the address or the micro instruction to be executed next when a branch is taken. Such a micro instruction is interpreted as follows. To execute the micro instruction, turn on all the control lines indicated by a 1 bit, leaving all the control lines leaving off all of the control lines indicated by a 0 bit. The resulting control signal will cause one or more micro operations to be performed, all the ones with a 1 bit associated with that. If the condition indicated by the condition bits is false, we execute the next micro instruction in the sequence. And then thirdly, if the condition indicated by the condition bits is true, the next micro instruction to be executed is indicated by the address field. So in this figure, figure 1913, it shows how these control words or micro instructions could be arranged in a control memory. The control instructions in each routine are to be executed sequentially. Each routine ends with a branch or jump instruction indicating where to go next. There is a special execute cycle routine whose only purpose is to signify that one of the machine instruction routines is to be executed next, depending on the current opcode. The control memory of figure 1913 is a concise description of complete operations of the control unit that defines a sequence of micro operations to be performed during each cycle, that is, a fetch, indirect, execute, and interrupt, and it specifies the sequencing of these cycles. If nothing else, this notation would be a useful device for documenting the function of a control unit for a particular computer. But it is more than that. It also is a way of implementing the control unit. The control memory of figure 1913 contains a program that describes the behavior of the control unit. It follows that we could implement the control unit by simply executing the program. So figure 1914 that we're showing here illustrates the key elements of such an implementation. The set of micro instructions is stored in the control memory. The control address register contains the address of the next micro instruction to be read. When a micro instruction is read from the control memory, it is transferred to a control buffer register. The left-hand portion of the register, so you can look at figure 1912A, if you like to, connects to the control lines emanating from the control unit. Thus, reading a micro instruction from the control memory is the same as executing the micro instruction. The third element shown in the figure is a sequence unit that loads the control address register and issues a read command. So let us examine this structure in greater detail as depicted in figure 1915, which we're showing here. Comparing this with figure 1914, we see that the control unit still has the same inputs and outputs. The control unit functions as follows. To execute an instruction, the sequencing logic unit issues a read command to the control memory to the word whose address is specified in the control address register is read into the control buffer register. The contents of the control buffer register generates control signals and next address information for the sequencing logic unit. The sequencing logic unit loads a new address into the control address register based on the next address information from the control buffer register in the ALU flags. All this happens during one clock pulse. The last step just listed needs a little bit more elaboration. At the conclusion of each microinstruction of the sequence logic unit loading a new address into the control address register, depending on the value of the ALU flags and the control buffer register, one of the three decisions is made. Get the next instruction, so add one to the control address register. Jump to a new routine based on a jump microinstruction. Load the address field of the control buffer register into a control address register. Or jump to a machine instruction routine. Load the control address register based on the opcode in the IR. Figure 1915 shows two modules labeled decoder. The upper decoder translates the opcode of the IR into a control memory address. The lower decoder is not used by horizontal microinstructions, but is used for vertical microinstructions. As was mentioned in a horizontal microinstruction, every bit in a control field attaches to a control line. In a vertical microinstruction, the code is used for each action to be performed, and the decoder translates the code into individual control signals. The advantage of vertical microinstructions is that they are more compact than horizontal microinstructions at the expense of small additional amounts of logic and time delay. So as was mentioned, Wilkes first proposed the use of microprogramming control units in 1951. The proposal was subsequently elaborated into more detailed design, and it is instructive to examine this seminal proposal. And so we see an illustration of what that was all about. The configuration proposed by Wilkes is depicted in figure 1916 here. So the heart of the system is a matrix partially filled with diodes. During a machine cycle, one row of the matrix is activated with pulses. This generates signals at those points where a diode is present, indicating by a dot in the diagram. The first part of the row generates a control signal that controls the operation of the process. The second part generates the address of the row to be pulsed in the next machine cycle. Thus, each row of the matrix is one microinstruction, and the layout of the matrix is the control memory. At the beginning of the cycle, the address of the row to be pulsed is contained in register 1. The address is the input to the decoder, which when activated by a pulse signal activates one row of the matrix. Depending on the control signals, either the opcode in the instruction register or the second part of the pulsed row is passed into register 2. During the cycle, register 2 is then gated by register 1 by a clock pulse. Alternating clock pulses are used to activate a row of the matrix and to transfer from register 2 to register 1. The two register arrangement is needed because the decoder is simply a combinatorial circuit with one register. The output would become the input during a cycle, causing an unstable condition. The scheme is very similar to horizontal microprogramming approach described in figure 1912A. The main difference is that the previous description of the control address register could be incremented by 1 to get to the next address. In the Wilkes scheme, the next address is contained in the microinstruction. To permit branching, a row must contain two address parts controlled by a conditional signal. as shown in the figure. Having proposed this scheme, Wilkes provided an example of its use to implement the control unit of a simple machine. This example, the first known design of a microprogrammed processor, is worth repeating here because it illustrates many of the contemporary principles in microprogramming. So here in this figure, 19.5 is a complete set of microinstructions expressed in symbolic form that implements the control unit. Thus, a total of 38 microinstructions is all that is required to define the system completely. The first column gives the address of each microinstruction. Those addresses corresponding to the opcode are labeled. Thus, when the opcode for an add instruction is encountered, the microinstruction at location 5 is executed. Column 2 and column 3 express the actions to be taken by the ALU and control unit, respectively. Each symbolic expression must be translated into a set of control signals. Columns 4 and 5 have to do with the setting and use of the two flags. Column 4 specifies the signal that sets the flag. For example, 1, the C's mean that the flag number 1 is set by the sign bit of the number in register C. Column 5 contains a flag identifier, then column 6 and 7 contain the two alternative microinstruction addresses to be used. Otherwise, column 6 specifies the address of the next microinstruction to be fetched. Instructions 0 through 4 constitute the fetch cycle. Microinstructions 4 presents the opcode to a decoder, which generates the address of a microinstruction corresponding to the machine instruction to be fetched. The reader should be able to deduce the complete functioning of the control unit from a careful study of table 19.5. And so keep that in mind. So the principal advantage of the use of microprogramming is to implement a control unit is that it simplifies the design of the control unit. Thus, it is both cheaper and less error prone to implement. A hardwired control unit must contain complex logic for sequencing through the many micro operations of the instruction cycle. On the other hand, the decoders and sequencing logic unit of a microprogram control unit are very simple pieces of logic. The principal disadvantage of microprogrammed units is that it will be somewhat slower than a hardwired unit of comparable technology. Despite this, microprogramming is a dominant technique for the implementation of control units in pure CISC architectures due to the ease of implementation. RISC processors with their simpler instruction formats typically use hardwired control units. Okay, well, that's it for this lecture. We've talked a lot in detail about micro operations, one level below the operands that we have talked about up to this point. We talked about microprogram control. We talked about how we can go about controlling the processor and consider the hardwired implementation ways of doing it. All right, well, thank you very much. That'll end for now.